All right, so today we're just going to review logs. So just like last video, this is just a overview / refresher. I'm not trying to teach you logs from scratch. Okay, so the first thing we should talk about is what is a log. So logs are basically just the inverses of exponents. So for example, we have an exponent. If we have 10 squared, 10 to the 2, that's obviously going to give us 100. And then a log asks basically if we have a log base 10, so our base 10 here, of 100, what is the exponent that we have to raise 10 to in order to get 100? So we have to raise 10 to the power of 2 to get 100, so our log there is equal to 2. So logs, as I mentioned, we have our base. So a here is the base. Just like with exponents, we have our base, and then we have the exponent here. So x in this case would be the exponent. And now this isn't a technical term, but I always thought of it, I always thought of this part as my answer because most of us are more familiar with the exponential form of equations. So I always think of the right-hand side here as my answer. So I think of this here as my answer. So the way when I was learning it, the way I remembered like what order the numbers go in basically, I have my log, then I have base, answer, exponent, and that corresponds to my exponential, which is easy to remember, where you have the base, exponent, and then your answer. So that's the way I always thought of it, base, answer, exponent. That's like the order that the numbers go in a logarithmic equation. Okay, so now let's just practice writing equations in logarithmic versus exponential form. So here we're going to change these log forms into exponential forms. So write in exponential form. Now here, we don't see a base written. So in intro classes like algebra, pre-calc, intro physics classes even, if you see a log without a base, it just refers to base 10. So if you see a log with no base, just assume base 10. So here we have 10 as our base. So the way we write this in exponential form would be 10 raised to the 1.4 power is equal to 25. Now log of 1,000 is equal to 3, so our base is again 10. So we have 10 raised to the power of 3 is equal to 1,000. Okay, so now we have a different base. So we have base 3, but we do it the same way. So we just have 3 raised to the power of 4 is equal to 81. And then for our final example, again, we have base 10, so we have 10 raised to the 1 is equal to 10. All right, now we're gonna go from exponential form to logarithmic form. So these, we have 10 to the 3 is equal to 1,000. So we can remember our log, base, answer, exponent. So for the first one, I have log, my base is 10 of 1,000 is equal to 3. Now I have 3 to the 3 is equal to 27. So log, the base is 3. The answer is 27. So it's 27 is equal to 3. So I have to raise 3 to the power of 3 to get 27. And now 4 to the 0 is equal to 1. So this is going to be log base 4 of 1 is equal to 0. So now we're going to talk about logs of 1s and 0s in a minute. Okay, and then our last one, we have log base 2 of 16 is equal to 4. So what power do I have to raise 2 to get 16? I have to raise it to the 4th power. Okay, now let's talk about the rules for logs. So just like for exponents, logs have rules when we combine them. So now here we have log of xy is equal to log of x plus log of y. So when we have multiplication, we add. Now here we have log of x over y is equal to log of x minus log of y. So when we have division, we subtract. And now these two rules might look familiar to you from exponents. Remember when we had, for example, x to the a times x to the b is equal to x to the a plus b. So when we have multiplication, we add. And then the same thing when we have x to the a over x to the b, we do x to the a minus b. So then when we have division, we subtract. And those rules are similar because logs and exponents are inverses of each other. So they're going to have basically the same rules. Okay, and then our last rule is that if we have an exponent in our log, we can just bring that out in front here and have a log x. So one thing to be careful of here is that when we write like log of x to the a, the exponent is on the x, not like the whole log of x. So we're not writing here like log of x and then raising that whole thing to the power of a. We're just exponentiating the x there. Let's say you see like 2 log 4 or something. I've seen some students write like log of 4 and then that whole thing squared. So that's not the case. You're not squaring the whole log of 4, just the 4 is getting squared. So it would just be log of 4 squared, which is equal to just log of 16. So be really careful of that. This coefficient goes on the argument of your log. But we'll do more of this when we do some examples. Okay, so then 2 more rules. So these 2 rules we can kind of figure out if you know exponents. So if I rewrite these 2 things as exponents, I can say a to the 0 is equal to 1, which we remember from our exponents, anything to the power of 0 is equal to 1. So this is just the log version of that. So any base you have here, log of 1 is always going to be 0 because anything raised to the 0 power is 1. And then log of a, when the base and the argument are the same number, is going to be equal to 1. So that's because if we have a to the power of 1, that's always going to give us that same number back, which we know from our exponents. So this is just a restatement of 2 things we already know, just in log terms. All right, now let's just do some easy examples with these rules. So here we just want to expand these expressions. So log of 6x, that's going to be log of 6 plus log of x, because these 2 are multiplied, so we can just write it as addition. And then, of course, log of 6 is just a number. So if you wanted to like plug into your calculator log of 6, you could do that and then rewrite it as whatever that number is plus log of x. And then, of course, since I haven't written a base here, we're just going to assume base 10. All right, then log of b squared over c. So let's break up the fraction first. So we'll do log of b squared minus log of c. So we've broken up that fraction first. And then now we can expand this term further. So now we have these 2 things multiplied. So we can write log of a plus log of b squared minus log of c. But we can also rewrite log of b squared, right? We can rewrite that as 2 log b. So now we can rewrite this whole thing. So this whole thing expanded out will be log of a plus 2 log b minus log c. All right, now we have log of x cubed times y to the 4th. So let's break up the multiplication first. So we're going to have log of x cubed plus log of y to the 4th. And now I can expand out the exponents. So I can rewrite this as 3 log x plus 4 log y. Okay, and then the next one, we have log of square root of x times y. So let's rewrite this as log of xy to the 1/2, right? Because we can rewrite the square root as the power of 1/2. So then I can put the 1/2 in front. So I have log 1/2 times log of xy. And then I can expand out the xy and write it as 1/2 log of x plus 1/2 log of y. Now it's important here when you go from this step to this step, both of these terms get the 1/2 because you sort of have like parentheses out here. So when you expand out your log of xy to log of x plus log of y, both of these terms actually get the 1/2, right? Because both x and y, you're taking the square root of both of them. Okay, and then our next one, we have log of x plus y. So this one, we can't expand any further or simplify in any way. Unless we know x or y, there's really nothing else we can do here. Okay, now for this last one, we're going to have log of a, and then we'll separate out the denominator, minus log of b times c. Now, to expand out this log of b times c, we have to be a little bit careful. So I'm going to open up a new page. So we have log of a over b times c, and we said that this is log of a minus log of b c. So imagine there are like parentheses around this log of bc. And then log of bc, we know we can rewrite as log of b plus log of c. But we see there's a negative sign out front, so both the log b and the log c get that negative sign. So when we rewrite the whole thing expanded, we have log of a minus log of b minus log of c. Now, we could have sort of just jumped right from here to this step by saying, okay, my log of a is in the numerator, so it's just going to be log of a. And then a is getting divided by both b and c, right? Both of them are in the denominator, so a is getting divided by both b and c. So therefore, both log b and log c should be minus. So that's totally fine as well. So you have to be careful when you have multiple things in the numerator and the denominator. The logs in the numerator will all be positive, and all the logs in the denominator will have that negative sign. So for example, if you had accidentally written log of a minus log of b plus log of c, because, thinking, okay, well, b and c are multiplied together, so it's plus log of c, that would actually correspond to log of a times c over b, because this makes it look like log of a and log of c are multiplied together, because it's log of a plus log of c, and then with just log b in the denominator there. So you have to be very careful with that. Okay, so now that is those examples. So now let's look at some common mistakes. So this first one is a very common mistake. We saw this in our previous example. Log of x plus y. I'll see a lot of students write that as log of x plus log of y. But remember, log of x plus log of y corresponds to log of x times y, not this. So this is as simplified, expanded, whatever. This is as far as you could take this. So there's no log rule that applies to something written like this. Okay, so this is wrong. Don't do that. The next thing I'll see is writing log of a over log of b as log of a over b. So make sure that you remember your log rules where it's written as subtraction actually. And then the other thing I see a lot is students like canceling out their logs. So they'll see this, and say, okay, well, I have a log in both the numerator and the denominator, so I can just cancel them out. So that's not the way logs work. Logs are functions, which we'll talk about more in a second. So since logs are functions, they're not like just numbers like a or b or whatever. You can't just cancel out logs. So make sure that you follow your log rules, especially this is probably the most common mistake I see. Okay, so this is wrong. Don't do this. All right, and then the last thing is we already talked about this when we introduced this log rule. Make sure you understand that when you have a coefficient in front of your log of x or whatever, it's the argument of the log that gets that exponent here. It's not log of that whole thing that gets exponentiated. It's just the argument of the log. Okay, so don't do this either. All right. So logs are functions. So that's very important to remember. So let's just draw the graph of a log. So this is like my x-axis, my y-axis, and we're just going to draw log of x. So the graph of log of x looks sort of like that. It does go all the way to infinity, so this portion of the graph here will just sort of get bigger and bigger, but very slowly, but it will eventually go to infinity. And then this point here, it crosses the x-axis at x is equal to 1, and we can remember that because we had log of 1 was equal to 0, and then it goes all the way down here to negative infinity. So one thing with logs being functions to keep in mind, when I write something like log of x, or when you see it in any book or whatever, there are parentheses that are being ignored. So you should really write log of x because, like we said, logs are functions. And when you write a function, you write f of x, you write it with parentheses. So we're sort of ignoring the fact that there are parentheses to show that log is a function. It's taking some argument, x or y, whatever it is. So that's why you might have noticed when we did these examples, some of them I wrote with parentheses and some of them I didn't. So it's okay to write it either way. The point is that it's clear what is in the log. So usually when you see something like this, like log of x plus y, you want to put parentheses around it, because if you write something like log of x plus y, it's not really clear. It looks like you're just taking log of x and then just adding y, as opposed to taking the log of x plus y. So in this case, something like this, you would definitely need to put parentheses. But for all these other ones, it's pretty clear what the argument of the log is. Usually you can get away with not putting parentheses, even though they're really there. Okay, so now let's talk about negative logs a little bit. So let's take our graph of log of x. Okay, so let's just right here, we have log base 10 of x. And this is going to be equal to the exponent if we were to write it as 10 to some exponent is equal to x. So what this first one tells us and what this graph here tells us is that if I raise 10 to any positive exponent, so it could be 1/2, it could be 2, it could be 4, it could be 100, whatever. If I raise 10 to any positive exponent, this number is always going to be greater than 1. And then this tells me that if I take 10 or any number and raise it to some negative exponent, I'm always going to get a number that's less than 1, right? So this will always be something that's less than 1, because, for example, if I do 10 to the -2, that's 1 over 100. If I do 10 to the -3, that's 1 over 1,000. So anytime you have the negative exponent, you're going to get a number that's less than 1. So that's all this is telling you here. And then, of course, as we saw before, if x is equal to 1, so if we have log of 1, that's equal to 0, because 10 raised to the 0 power is 1, or any number raised to the 0 power is 1. So that's where that it crosses the x-axis there. Okay, and then we also see that the log graph, there's nothing on this left side of the graph here. So if we take a log of like -4, that's undefined. So logs of negative numbers are undefined. And that's because if I do like 10 to some exponent, how can I get a negative number from that? Is there any exponent that I can raise 10 to get a negative number? There's not. So that's why the log of a negative number is undefined. And then the same thing goes for log of 0. So if I have 10 to some power, can I ever get 0? Like, what number can I raise 10 to get 0? There's nothing that satisfies that equation, so the log of 0 is also undefined. Okay, and then let's talk about natural logs for a second. So as we saw before, base 10 is the most common in intro-level math and physics courses. So anytime you see log, you can assume that the base is 10 if you're in an intro-level course. Once you start getting into more advanced courses, you'll see the natural log. So the natural log is just a regular log, but with a specified base, which we call e. So e is equal to 2.718. It continues forever, and it's called Euler's number. Be careful to pronounce that Euler, not Euler. So it just has a special base. So log base e is what we call the natural log, and you'll usually see it denoted as ln. And it behaves the exact same as any other log. If you have ln of e, that'll give you 1, because e raised to the power of 1 will give you e, and then you can plug in any numbers you want there. So it's the same exact thing as a regular log, but just with a specified base. And then another thing to keep in mind is once you get to like really advanced physics courses, anytime you see log, they're referring to the natural log. So if you're reading like a physics paper or something and they write log, they really mean base e, not base 10. So in intro courses, When you see log, it refers to base 10, and then as you get more advanced, it kind of switches to referring to the natural log. Okay, now let's just do some last examples of expanding out and using the log rules. So here we have, we'll do the numerator, so we have log of A plus log of B. And then this is divided by log square root C, and log square root C we can write as C to the 1/2, and log of C to the 1/2 we can write as 1/2 log C. Okay, and now we have a similar problem here. So now we have log A, and now our B is in the denominator, so we have minus log B, and then our square root C is also in the denominator. So again, we have minus the 1/2 log C. Okay, this one we have log of 1 minus log of A squared, which we can write as 2 log A. And now log 1, we know what that's equal to, right? We know that log of 1 is equal to 0. So we can sort of just erase that term. And this is just equal to negative 2 log A, right? All right, and now our last one, we have a natural log. So natural log uses the exact same rules as log. So we have ln, we'll write this as 6xy cubed. And then that whole thing is in a square root, so it gets a power of 1/2. So we can rewrite this as 1/2 ln 6 plus ln x plus 3 ln y. And then if you want, of course, you could distribute out this 1/2 to each term. So you'd have a 1/2 in front of the ln 6, 1/2 in front of ln x, and 1/2 in front of 3 ln y. Okay. And then we just have 3 more problems, and that's it. So this one here, log x squared, that's going to be 2 log x. And then we have minus log y in the bottom. And then we also have minus 3 log z in the bottom. And now this one, we have another natural log. So we have ln of ab to the 1/2. So we put that 1/2 out front. We have ln A plus ln B. And of course, we can distribute the 1/2 to both and get 1/2 ln A plus 1/2 ln B. And then our last one, we have, take this one step at a time, we have log x plus log y over z to the 1/2, right? Because the y and z are in the square root. And now we can expand out this term. So we have log x plus 1/2 log y minus log z. And then I can distribute out the 1/2 to both the log y and the log z and get 1/2 log y minus 1/2 log z. Okay, and that's it. So the next 2 videos will cover logarithmic and exponential functions, and I'll see you guys next time. Logs from scratch. This video is just going to be a overview / review of logs. I'm not trying to... All right, so today's video is just going to be a overview / refresher of logs. The first thing is, what is a log? So, do you want to learn? Do you want to know what a log is?